our topic for today is what is the capacitance of a capacitor when instead of vacuum we have some dielectric inside it. For example, if this is a parallel plate capacitor, what if we have a slab of a dielectric with dielectric constant K inside it? What will be the capacitance? So we'll analyze this. I'm not going into the physics of dielectrics, you can see it in any book. We'll understand the behavior, how dielectrics behave when put inside a capacitor. See, let's say this is our capacitor. You have to understand it. This is a parallel plate capacitor. Let this be positive. So this will be minus. Okay. For the time being, consider this to be vacuum inside this. So what we have, if the charge is plus Q on this, this will be minus Q. Let the area be A. So we have sigma, that is surface charge density on this plate and this plate equal to Q by A. Okay. Now, second thing we know about this is electric field. Electric field inside this, let this be 0, that is with vacuum. So sigma 0, and this is E0. What is electric field inside this? You know, it is sigma by epsilon 0. Sigma by 2 epsilon 0 because of this, and sigma by 2 epsilon 0 because of this, both in same direction. So it is sigma by epsilon 0. The direction is from plus to minus, that you know. Okay. So this is E0, and potential will be V is what? Q by V is C. Q by V is the capacitance. So V is Q by C. Okay. You have these relations. I'm just revising, giving you a recap. And one more relation we have about capacitance, that is epsilon 0 A by D, where D is this distance. Okay. So this is when we have a vacuum inside this capacitor. Now, let's say this is not a vacuum. Instead of vacuum, what we have done is we have put a dielectric inside it. The dielectric constant of which is K. And what is dielectric constant? K. It is defined as E0 by E, where E0 is the electric field intensity in vacuum and E is the electric field intensity due to the dielectric. That is dielectric constant K. So K is E0 by E. So what happens? So this is plus. So obviously minus will appear here. And this is minus, so plus will appear. That is, if the surface charge density on this sheet is sigma 0, we'll have another surface charge density, that is, we'll have another charge accumulation on the surface of the dielectric. Let's say that is sigma K, denoting surface charge density of the dielectric. Okay. Obviously, it will reduce the electric field. Clear? Now, let's analyze it using these figures. Now the electric field inside this dielectric slab will be, it will be E0, that is the original one, minus electric field due to K. Okay. So what we can do, we know K is E0 by E. So E will be E0 by K. From here, E0 is what you can write. E will be E0 by K. So that is E0 minus EK. Let's put it on one side. So we'll put it here. So you get EK equal to E0 minus E0 by K. That is, if you take E0 out, 1 minus 1 by K. From here we have a relation between E0 and EK. E0 by EK will be K by K minus 1. So this is a relation between the two electric fields, where E0 is the electric field without this dielectric, that is in vacuum, and EK is the electric field inside this dielectric. Okay. Now, what we can write is, and E0 can be written as sigma 0 by epsilon 0, and EK can be written as sigma K by epsilon 0, that is K by K minus 1. from here what you get is sigma 0 by sigma k, that is the surface charge density on this, and this, the ratio is this. Okay, this is the second relation that you get. And finally, you know, sigma is what? It is q by a. Sigma 0 is q by a, and sigma k will be qk, let's say, the charge on this dielectric by a. So this is also directly proportional. So from here you get this q0 by qk. This is 0, so this is k by k minus 1. So when you insert a dielectric in a parallel capacitor, parallel plate capacitor, these are the ratios: electric field ratio, surface charge density ratio, and this is charge ratio. So you understand this? Now we'll see what will be the capacitance if a dielectric slab is inserted inside a capacitor. When we inserted a dielectric slab, we saw the ratio of surface charge densities, charge and electric field. Now let's see like this. If this is a parallel plate capacitor and we have first, let's see this first example. This is your parallel plate capacitor. This is plus q, this is minus q, and we have this thickness as d1, this thickness as d2. This is your dielectric, and this thickness again vacuum, that is d3. Okay, so what we will have, see, electric field intensity here will be E0, and electric field intensity here will be by definition E0 by k, and electric field intensity here will again be E0. Because of this electric field intensity, we will have voltage here, let's say V1, then again voltage here V2, and again voltage here V3, and this complete voltage will be V. Clear? So we have V equal to V1 plus V2 plus V3. Clear? V can be written as Q by V is a constant, that is C. So V can be written as Q by C. So I am writing it is Q by C, the net capacitance. Now this is V1 plus V2 plus V3. V1 is what? It is E0 into D1. Then V2 is what? E0 by K into D2, and then E0 D3. Clear up to this? And you know from Gauss's law, you know this is what? It is equal to Q by A, that is sigma by epsilon 0. This you know. So from here what you get is Q by epsilon 0 A D1. Then you have okay. So what you get, if you take common Q by epsilon 0 A as constant, you get D1 plus D2 by K plus D3 by, no, nothing, D3 by nothing. This is what you get. And Q is what? Here you have this as Q by C. Okay, so Q cancel. From here what you get? You get C will be, this we have to find, it will be epsilon 0 into A by C, D1 plus D2 by K plus D3. This is capacitance. So we have found the capacitance. Sometimes D1, D2, D3 won't be given. It will be given that the gap between the parallel plate capacitor is D, and we have introduced a dielectric of thickness T. So this what means? This means T is equal to, here we have taken D2. Okay. So D1 plus D3, what you can write? D1 plus D3 will be, D1 plus D3 will be D minus T. Clear? Because D1 plus D3 plus D2, that is equal to D. So this is D minus T. So you can put it here. You will get epsilon 0 A. This is D1 plus D3. So D minus T plus D2, that is T by K. So this way also you can write. So this can be actually generalized. If instead of one T, if you have many slabs of let's say thickness T1, T2, T3, T4. This can be generalized. How the generalized expression can be like this: D, that is the distance between the slab, minus, see, this will be T1 plus T2 plus T3 and so on, plus T1 by K1, T2 by K2 and so on. So this can be generalized like this. You should keep this in mind. You'll, in objective questions, you won't have time to derive this expression. You'll use it directly to find the capacitance. Let's say a question. A parallel plate capacitor contains two dielectric slabs of thickness 1 mm and 0.5 mm. This means it has no vacuum. We can assume it. So this is, let this be the sheet. Then this is your first dielectric slab 1 mm. Its K is equal to 8, and then you have second dielectric of 0.5 mm. Its K is 2.5. Okay, so this is your parallel plate capacitor. Maximum electric field intensity that the dielectric with lowest electric field capacity can handle is 6.4 into 10 to the power 6 voltmeter. That is, this and this, we have two dielectrics. Let this be the dielectric which has the lowest capacity of handling electric field intensity, and that maximum value is 6.4 into 10 to the power 6. That is to say that the maximum electric field intensity can be 6.4 into 10 to the power 6 volts per meter inside this. Okay, so the question is, what is the maximum voltage across C? See, voltage across C, this is V1 plus V2. So we'll have V, we have to find V, which is V1 plus V2. And this is, if E1 is this, then E1 into this 1 mm, let's say D1, and E2 into D2. Now E1 is what? You can write E1 as E0 by K1 D1, then E0 by K2 D2. And it says it can handle, maximum it can handle 6.4. So we'll put this value here. So V will be E0, that is 6.4 into 10 to the power 6 volts per meter. I'm taking it out like this, E0. Then we have D1 by K1 plus D2 by K2. So what do we get? We get D1, thickness is 1 mm, that is 1 into 10 to the power minus 3 meters by K, that is 8. Then you have 0.5 into 10 to the power 3 meters by 2.5. Okay, so what do we get? We get 6.4 into 10 to the power 6. This is 1 by 8, that you can write as 0.125, because 0.25 is 1 by 4, so by 2 is 0.125, and then says 1 by 5, that is 0.2 into 10 to the power minus 3. So what do you get? You get 6.4 into 0.325 into 10 to the power 3 volts, that is kilovolts. Let's find the value. What is 6.4 into this? So you roughly get 2.08 kilovolts. Okay. Now let's see. We have a parallel plate capacitor. It is filled with a dielectric which has constant, dielectric constant is 3.4. We connect it to a battery of 100 volts. That is, it is charged up to a voltage of 100 volts. Find capacitance and potential energy, electric potential energy. This is the first part. Second part is, we remove the dielectric from the capacitor, leaving everything as it is. Now what is the capacitance and what is the potential energy? Let's see. You know, capacitance, if I write like capacitance with a dielectric is this, it is equal to K times without this, when it, that is a capacitance with vacuum inside the parallel plate capacitor. So this is the relation. We have seen several concepts, you can find this. So this is very easy. Now, because electric field gets divided by E0 by K, so this is proportional, and so we get this. Let's find out what is the capacitance when we have dielectric. So this is epsilon 0 A by D and multiplied by K. So this will be 8.85 into 10 to the power minus 12. Area is 4 meters square. Then we have D. D is 4 mm. So 4 into 10 to the power minus 3. And then we have K. K is 3.4. So let's calculate this. So this comes to roughly 3 into 10 to the power minus 8 farads. Okay. Now we have to find the potential energy. For potential energy, we need to know voltage, that is half CV square. What will be V? What is potential energy with the dielectric? It will be half C, that is this, V square. V is 100 volts, that is 10 to the power 2 square. So this is 10 to the power 4. So what do we get? This is 3 by 2 is 1.5, that is 1.5 into 10 to the power minus 4 joules. This is your potential energy. So we got capacitance with dielectric and we got potential energy with dielectric. Now let's see if when the dielectric is removed, leaving everything as it is, now we have the relation Ck is equal to Kc0. So C0, that is capacitance in vacuum, will be Ck by K. Ck we have this, so this by K, 3 by 3.4 into 10 to the power minus 8. So this is your capacitance. And what will be the voltage? Voltage will be, see, charge will remain same. Charge will remain same. This means Q by V is C. Now, charge will remain same. This means initial charge, if it be because of K, so that will be K. This will be equal to this. What was this? This was C K into V, that is 100. And this is equal to CKVK. So this will be C0 V nu V. This we have to find. We know what is VK. Now CK, see, CK by C0. CK by C0, if you put it, so you will get K is V is equal to CK by C0. CK by 0 is K, K, VK. That is 3.4 into VK was 100 volts. So what you get is voltage is 340 volts. Now you have C0, this, and you have voltage. Now you can find half CV square. You will get the potential energy when dielectric has been removed. Okay. We know when capacitors are connected in series like this and so on, C1, C2, C3, the net capacitance is, if it is 1 C, we have this relation, that is equivalent capacitance will be like this. And when we have parallel, connected in parallel, we have capacitors connected in parallel like this, C1, C2, C3, equivalent capacitance is C1 plus C2 plus C3. This we have already read and we have solved some question. What when dielectric is filled inside a parallel plate capacitor? Let's see. This is a parallel plate capacitor. Okay, this is A, this is B, the terminals. Let's say we have one dielectric D1 K1, then second one D2 K2, then third one D3 K3, and then this one D4 K4. Okay. Now you can see this can be taken as one dielectric, one capacitor. Let's say this is C1. What this will be? It will be epsilon 0 K1 A by D1. D1 is the thickness of this and A is area. Similarly, C2 will be K2 epsilon 0 A by D2. So this way we have C1, C2, C3 and we can visualize it like this. Capacitors connected in parallel. This is B, this is A, this is your C1, this is your C2, this is C3, C4. That is, this capacitor is connected in series to this capacitor. Again, this is connected in series to this and this. So these four, we can visualize it as series connection of four capacitors. And then you know how to find the equivalent capacitance. This is 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4. Clear? Where you know how to find C1. The area for all of these dielectrics is same, A. The thickness is changing. Clear? Now, let's see when they are connected. This is, if this is vertical, then when they are connected horizontally, then what? This is clear to you, I guess. Now, if this is our capacitor this is point A and this is point B. Let's say from here to here we have, this is first dielectric, area is, let's say, A3, this area is A2, this area is A1, and D is common for all. Their area was common, thickness was different. Here this gap is common, area is different. So this is, let this be K1, this be K2, this be K3. Now here what we'll have, if you think this is C1, C1 will be K1 into epsilon 0, area is different, A1 by D, D is common. C2 will be K2 epsilon 0, A2 by D, and C3 will be K3 epsilon 0, A3 by D. So you find C1, C2, C3, and all of these have common potential. That is, they can be visualized as three capacitors connected in parallel, like this. This is your C1, this is your C2, this is your C3. Okay, this is A, this is B. The terminals are like this. So what you get is, not V, C will be, equivalent capacitance will be C1 plus C2 plus C3. You know what is C1, what is C2, what is C3, you can add them all and get the equivalent capacitance. Clear? Although the concept is very clear, let's see a simple example. We have to find the capacitance in terms of C0, where C0 is without any dielectric. Say this one, I told you C1, this is in series connection, so C1 will be epsilon 0, let the area be A, epsilon 0 A into K1 by D1, okay, and C2 will be epsilon 0 A by D2 K2. And what is C0? C0 is epsilon 0 A by D. Clear? So we have 1 by C equal to 1 by C1 plus 1 by C2. So this will be equal to 1 by epsilon 0 A K1 by D1 by plus K2 by D2. This is your 1 by C. Now if we have to put in terms of C0, what you can do is epsilon 0 A, you can put it as D into C0. So we can write it as 1 by D into C0 K1 by D1 plus K2 by D2. Okay, so this is for this capacitor. Now let's see for the second capacitor. For the second capacitor, C1 will be K1 epsilon 0 A1 by D, and C2 will be K2 epsilon 0 A2 by D, and your net equivalent capacitance will be, this is, these two are in parallel, so C1 plus C2, that is K1 A1 can be taken out plus K2 A2 into epsilon 0 by D, and we know that C0 is epsilon 0 A by D. So epsilon 0 by D, you can write it as C0 by A. So you have C in terms of C. Clear?